aspects of mechanical engineering, one of the most important of which is turbine vibrations. Now, most students get a taste of vibration analysis in their studies, but today we're going to get you grounded on complex vibrations. So sit back, buckle up, and get ready for takeoff. So before we get into the more complicated multi-degree of freedom system, we're going to have Pete here go over the response of the two-mass system.
Sounds great. Let's head to the lab.
Here we have the first of two modes for a two-mass block system. This is the in-phase mode, meaning the amplitudes are in the same direction. At a different frequency, we can see the second mode, where the blocks vibrate out of phase, meaning that the amplitude is opposite each other. A two-degree of freedom system with two modes can be used to represent many everyday systems, such as jumping on a trampoline. However, turbine blades are higher order systems, and are thus more complex.
Using finite element analysis software, such as ANSYS APDL, researchers are able to evaluate the modes and responses of turbines. A bladed disc is comprised of sectors, which include one blade and its disc portion, and this disc also exhibits cyclic symmetry about the axis of rotation with these sectors. Using this symmetry speeds up the calculation of the modes and the mode shapes in the analysis. There are several different motions that can occur in vibrations of these bladed discs. These can include flex bending, torsion, stripe bending, and edgewise bending. Seen here is the first mode that occurs for this bladed disc. It occurs around 2.2 kHz and is known as the first bending mode because it bends across the blade. Notice all blades are in phase with each other. This lets us know that we are in the first harmonic of the system. By increasing the frequency, different kinds of vibrations can occur. Shown here is the torsional mode in the first harmonic, called so due to the twisting motion of the blades. It occurs around 6.7 kHz, and notice that the blades are also in phase with each other. The exact same kinds of modes occur at slightly different frequencies from the first harmonic in higher harmonics. This is called a high modal density, as many harmonics occur at similar frequencies. These harmonics introduce a nodal diameter, seen here in the first mode, second harmonic, occurring slightly over 2.2 kHz. A nodal diameter is a line stretching across the entire disk that has no response. Notice that the two sides of the disk are out of phase with each other now. Increasing in harmonic number increases the amount of nodal diameters up to half the number of sectors. This pattern occurs for every mode as well, as seen in this third harmonic torsion mode. We can group the same mode in each harmonic as a mode family that share a similar frequency. As frequencies increase, the vibrations of the system become more and more complex, as seen here.
In summary, real systems vibrate with complex behavior. Airplane turbines vibrate with specific modes at certain frequencies, leading to high modal densities. And understanding this complex behavior using a tool like FEA helps us improve everyday systems.
So the next time you fly from Dallas to Boston, make sure you thank a local mechanical engineer for analyzing the turbine vibrations.